So we are joined by Dr. Sungduk presenting his research coupling global climate models with neural network cloud emulators. Dr. Yu is a project scientist at the University of California, Irvine, specializing in developing and integrating machine learning algorithms for Earth system models. He earned his PhD from the University of California, Irvine, and explored multi-scale climate modeling frameworks and the global energetics of the coupled climate system. His postdoctoral work at Yale University delved into the predictability of extreme El Niño events and tropical climate dynamics, broadening his expertise in climate science. Thank you.
Hi everyone. I'm Sungduk from UC Irvine. Today I will give you the update on ClimSim2. So ClimSim2 is basically the second phase of ClimSim. And since there may be new members that live, so I will give like brief background, like why we are doing this. So maybe I'm beating dead horse for this crowd. Basically in the current generation global climate models or system models, the largest or number one, the error source is coming from the cloud processes. Basically, the GCM grid is too large. We are approximating the cloud processes. So that's the big error source. So ideally we want to go very high resolution global climate model, but our the currently available supercomputers doesn't allow us to use like such high resolution model like for the decadal or centennial simulations. So maybe 20 years ago, the modelers came up with like new idea, MMF, multi-modeling, multi-scale modeling framework. This is just like interim solution, to represent cloud process better. So hoping we can ultimately reduce model errors like coming from this inaccurate cloud approximation or parameterizations. So what MMF does is basically we are replacing those approximation with explicit numerical model called CRM, cloud resolving model. So this way we can cut some like assumptions like we have been using in the parameterization. So we can increase the fidelity of the calculation. The problem is the CRM has like smaller grid size, and to keep the numerical stability, the time step size like should be smaller too. So what that means is this MMF simulation is possible to use for climate scale simulations, but it's still too expensive, like for using casually. So our target is basically we want to emulate this embedded the cloud resolving model with the neural network so that we can hit what is it like, hit two birds. Like one is like the speed of the climate model, and then another bird is accuracy. That's what we are doing. So we are calling this hybrid physics machine learning climate model. So I already explained why we are doing this. So in hybrid climate model, basically it's hybrid, like physics meaning like traditional physics-based like climate model, combined with the machine learning data-driven emulators. So we have been trying this like for many years. The problem is that once we do this, and it ends up, in most cases, like with realistic like operational configuration, it ends up like blowing up. And what's the challenge? And to begin with, the target physical system, we want to emulate the clouds. The system is highly complex, and on top of that, there are many layers of technical challenges. The first, like running GCM, depends on HPC system, and which made the HPC may not be easily accessible, or maybe not familiar to the many researchers outside the climate science domain. And even then, we need the deep expertise in the climate model code to navigate millions of lines of Fortran code, like to identify the right input and output variables and how to wire this the machine learning emulator inside the Fortran code. And yeah, that's the next point. Yeah, the linking basically, there's like no easy way to link the Python program to Fortran program. And yeah, this is why we are doing ClimSim. We want to open source, remove all these entry barriers, and to open source this like key, very important, high impact climate modeling challenge to the public. So the ClimSim1, yeah, our focus is like to carefully generate and curate the data set, the benchmark data set, so everyone can like jump in and start to build emulators. So we had great success with that. And ClimSim2 is like we want to provide a minimal test bed. Minimal meaning not in like functionality, but like easy to use, yeah, easy to use, like test bed for downstream hybrid tests. Like what downstream hybrid test means is like ClimSim1, we tested like these emulators outside the climate model. So it was tested offline, but yeah, it's only like half of the work, and the real work is testing this emulator inside the climate model. That's why we say like downstream hybrid model. So yeah, our goal is like make easy to use, like lightweight test bed, yeah, to recreate the model flow reliably. So I'm happy to announce that a prototype test bed is ready. And it's lightweight, it requires only 2 nodes, and meaning that it's possible to deploy this into the cloud platform. And it's really easy to configure the machine learning model options, because I wired all these machine learning model options like into name list variables. And I also implemented like some optional like functionalities, for example, partial coupling scheme, which I will explain later. And also, yeah, it support ensemble inference, but it is not complete yet. We are currently and like most important, it's not yet architecture agnostic, yeah, due to some limitation in Fortran Python libraries. So we are currently working with NVIDIA's software engineers to make this testbed architecture agnostic, and also other functionality we working on is non-local information access. But what I mean by non-local is non-local in time and space. Yeah, maybe we want to incorporate the information from the previous time step as memory, or we can incorporate information from adjacent grid column to resolve like the local cloud process. Anyways, yeah, using this the prototype test bed, I will show you some results I have. So this is set up. The host model is E3SM. The emulator architecture I could use as an MLP. And for MLP, I tested like 30 top performing models out of 10,000 candidates that I tested like during the hyperparameter optimization. And input output variables, I'm using the full set, not subset of ClimSim variables. In the main text of the ClimSim paper, we have like 6 baseline models, but those are based on a subset emulation. But yeah, this MLP, we use all the variables provided by ClimSim, yeah, which is key requirement like for the operational use. And yeah, let's jump in. So I'm showing you the time series of surface temperature and global average on the left, maximum in the middle, and minimum on the right. And the reason why I'm presenting minimum and maximum is that the model blow up usually triggered by one grid cell and whose state drifting to unrealistically low or high values. So that's why I'm showing maximum minimum. And you are looking at this gray area. So I configure neural network emulator turn on from day 2. So the gray shading is marking the first model day when neural network is not used. So the gray area for 70 time step, yeah, still the regular MMF or superparameterization is being used. And once MLP is turned on, this like white background, we can see the model blow up very quickly. Yeah, out of like 30 simulation, all models like crash at somewhere between 6 to 8 times steps. Looking at the spread across 30 the MLP models beyond the gray shading area, we can guess that there are multiple pathway of model crash. And there's like little more analysis, but I will not show in this talk. And also, I've done like a few other things, and our previous work showed that the ensemble prediction can stabilize hybrid simulation. So I tested ensemble MLP models, but it didn't help. And I suspect there could be possibly like some quirks in the initial condition. So I tested like 5 different initial conditions, but it didn't help. And with like certain initial condition, it could crash like as early as 4 times step. Yeah, so looking back, the early model blow was not really a surprise. And this offline model evaluation chart shows that the model skill varies a lot, one variable to another. In particular, there are many output variables like whose R-squared value is negative, 0 or negative. Like the lower bound is 0. I just cut up like this like variables like that doesn't show the bars. Basically, it has like negative like something values. But like one thing I wanna point out is that R-squared might not be the best metric like for patch data, for example, the precipitation or like the cloud condensate. But still, the main point of this slide is that there's a large divergence in model skills, like depending on the variables we want to predict. Oh, by the way, there are 4 different bars. They basically they are the MLP model with like 4 different configuration, but they are all MLP. Yeah. So this chart, here basically there's a red line marks like 3D or vertical result variables, or like 2D surface variables like left and right. And you can see like largely this 3D variable lacks the model prediction skill. So like from here we can hypothesize the maybe partially coupling skillful output variables only would lead to a stable simulation. So I designed a partial coupling scheme, which I will show you here. So think this black box represents the global client model, and this global client model contains like many subroutines. But one named fees run 1 is the subroutine that takes care of cloud processes, like for example, like MMF. And the input is from like some other subroutine, and the output is like to next subroutine. So they're like constant like data stream. So ClimSim targets to emulate this fees run 1 routine that wraps expensive cloud reservoir model. So the hybrid testing I presented earlier is doing exactly this, bypassing the original fees run 1, but feature one is represented by neural network emulator. So partial coupling scheme, the original subroutine, original MMF or super parameter subroutine and machine learning emulator subroutine runs in parallel. But after that, there is a mix and match of the output variables. So let's bring the R-square chart back. So for example, we are using variables in the black box from original subroutine MMF because neural network doesn't have any skill. And why we are using variables in the magenta box from emulator. And this specific configuration called surface-only coupling in the next slide. Yeah, so using this partial coupling scheme, I tested multiple partial coupling configuration. And black circle means the variable from the original subroutine, and magenta circle means a variable from the original, the MMF subroutine. So generally speaking, as you move from left to right, the more emulator variables are used. Yeah, so first configuration is like surface only, and the next column we are adding the momentum tendency, and the next column we are adding cloud condensate, basically the ice and liquid condensate tendencies. Or yeah, from there we add like heating temperature and moistening tendencies. And the last one is all. This is like the control simulation, the coupling or variables. We already saw the result of it. And there's a lot of figure generated, but I will show you like this summary figure. So I'm showing a simple metric of the hybrid simulation stability. And so my metric choice is the number of timestamp until model blow up. And the first good news is hybrid simulation using only surface variables from an emulator as stable, at least for 7 days. And while the timestamp goes only up to about 500, but that's because I set the duration simulation like for 7 days. So it could complete 7-day simulation successfully. And second, bad news, once we start to add vertical reserved tendency variables, hybrid simulations become unstable. However, the different the tendency variables destabilize hybrid simulation at different rates. Yeah, so if you compare these three, you will see that yeah, the cloud content tendency is the most important, yeah, the blow up factor, and momentum tendencies, yeah, it's also it affects, but like it destabilizes at like much like slower pace. And this one brings to the last slide. Yeah, so the summary, yeah, the minimal test bed is ready. If you wanna have a look, yeah, go to this GitHub repo and yeah, see the commit history. And from MLP test result, yeah, we can see that coupling surface variables are stable. But coupling tendency variables is like destabilizing simulations. And from here, yeah, what's next? Like we need to improve the test bed, like to make it release ready. The most important item is implementing architecture agnostic Fortran Python libraries, which we are currently working with NVIDIA software scientists. It's really hard like task. I have tried to like do this by my own, but like the managing scalability and memory management, like yeah, like was really hard. It's beyond my skill set. So I'm working together with these dedicated software engineers. And yeah, the porting to cloud platform, I think this is very doable because I personally have run the CSM on the Amazon cloud using like 2 nodes. So I think possibly we can start to work on not containerizing, but like porting to your cloud platform. And then another thing, we even without the test bed, could be, yeah, we can like try to improve the models, yeah, to have like better skill in predicting tendency terms, and there are many ideas like untested. Yeah, we haven't imposed physical constraint, and also we can try causal pruning, or we can try to incorporate like non-local informations, or another way could be in hybrid model, maybe we can do some kind of post-facto correction. Like once we have the prediction value from the emulator, and before we couple it to the climate model, maybe yeah, at that point we can like impose like some physical constraint, or we can limit the prediction values by the percentile or whatever threshold. And just like one last quick slide. Yeah, so this is the GitHub. And if you really, going to, this repo and look at the commit history, there's a whole bunch of commit history, but you just need to, focus on, these two commit, adding my FKB implementation from something. So yeah, these two commit contains like all this emulator implementation inside ITRSM. That's it. Thank you.
Thank you. Does anyone in the room have a question? I'll pass the mic over. Great.
Nice. Hi, Sungduk. It's Robert. Congrats on your new gig. I wanted to ask, is it possible to run this on such low computing resources on 2 nodes because you've got very low resolution, large scale dynamics? Because I normally think of the dynamics as taking, I don't know, a third or a half of what the physics takes, and E3SM normally has a much larger computational burden than 2 nodes. So I'm wondering how you pull that off.
Oh, yes. We use the raw resolution dataset version, and then in practice, this low ClimSim dataset is like super low resolution. It only has like 384 columns like globally. That's why we could like save like computation time.
Any questions online? Feel free to unmute your mic or use the raise hand function first. We'll start with another question in the room.
Could you speak a little bit more about, like how the time taken to simulate changes when you start coupling? Like you have like previous slides and the one like 2 slides before this, like you go over, here, in the next one. Sorry, the next one. Oh yeah, here. So here, like, could you speak about how, like coupling those particular variables like reduces, the time taken for this simulation? And sorry, go ahead.
So are you asking some like physical mechanism like
No,
behind
the computational time? Like you're like trying to reduce the computational time that like you basically speed up your computation because you have like coupled your neural network with like a physics-based simulation.
Oh, I see. So basically, doing this like partial coupling kind of what is it like defeat the benefit of like computational cost saving by using emulator instead of the original, the multi-scale modeling framework. So the partial coupling is only like for the developing the hybrid like model development process. Like I'm using this partial coupling to understand which variables are the weak point of the current hybrid model. That's why I'm using this partial coupling. And in this case, there's like no the computational time saving benefit. Actually, did impose like little more because there's like one more subroutine you need to run. But yeah, ideally, yeah, you'll be like this. Yeah, once we have like the nice emulator that's accurate and stable in hybrid setting, then yeah, we will 100% bypass this original the MMF subroutine. Yeah, in that case, yeah, we will attain like huge computational like cost saving.
Sorry, one more question. So if you go back to that slide, like the one which we were talking about before, you show that it blows up, or rather, like, yeah, time step will blow up, right? There's like 100, and then there's like 10. So when you say blow up, do you mean to say that that particular set of variables, machine learning plus physics-based model, they're like giving you like accurate output until the time it blows up, or does it like, so basically it's like an accuracy question, like is this are these models like accurate until the time they blow up, or like till when are they accurate?
Yeah, so yeah, that's a good point, because like stability is just like one part of the equation. Like the other important like thing to attain is the accuracy. So like inaccurate, like stable simulation, I mean model, yeah, kind of pointless. But anyways, yeah, going back to your question, this surface coupling, the surface only coupling, yeah, this one, the simulation quality is quite okay, at least for 7 days. But then on caveat is there could be like very slow drift of state, yeah, that eventually that crash the model. But at least yeah, for 7 days it looks good. But the rest, even I mean within like this like about 10 times step, within 10 times step, like until blow up, the similar quality is really bad. Yeah, they are exponentially drifting, and the first time that is already looking a little bad, and they not gradually, like exponentially, like getting worse and worse, and eventually like I don't know how many, but like yeah, like several the grid, like local grid column like goes into their state, like goes into like negative like Kelvin temperature. That's why it says like causing negative Kelvin temperature, and mother blows up. Like mother says like, oh, it's not possible to have a negative Kelvin, so I'm stopping the simulation. But anyways, yeah, the simulation quality is bad. All this like all like crashing like configuration, yeah, the simulation quality is really bad. I think Mike, you have something to add?
I was just gonna make some remarks, only if there's not any other questions though.
No, go ahead.
Okay, cool, yeah. And so Sean, I add a couple more comments here. The philosophy here is maximum complexity, emulating everything, radiation, convection, microphysics, etc. Which you could also do as coarse graining in time. If you want to separate processes, you're not coarse graining in time, and therefore you're leaving computational gains on the table. So it's kind of intentional, but it's very difficult. These kinds of crashes are familiar to me. It's representative to what I've seen in real geography limits when people are trying to emulate everything, and especially when you try to emulate the microphysical tendencies, assuming you want the host model to affect the resulting condensate. There's ways to cheat on that can give you better results, but we're leaning into the hard problem. In terms of sanity checks, the first thing you check is, what does it look like the first time step after coupling? It looks okay. And if Sungduk's looked at that, there's a whole ream of figures you can look at if you're interested. But then of course, it finds places that weren't in the training data set or something and goes out of sample. Maybe that's what's going on. What's really cool is that you've got the super parameterization running alongside it, and you can see it's trying to correct the problems. What the super parameter is trying to do is often trying to the opposite of what the neural network is doing as we approach these failure modes. And that's a new information signal that I think would be really interesting to do machine learning on. So as you do hundreds or thousands of these tests that blow up, you have this additional training set that maybe you could use to fine-tune the model or use for a creative reinforcement learning approach. And on the physics side, of course, there's many things you could do more intentionally than a brute force MLP. You know, things like DJ and Andrew Gittleman have done for the condensate field, you know, classifiers of non-zeroness upstream of regressors, physical constraints, etc. So there's a huge scope of things that could be done with this test bed. And if you're interested in getting involved, shoot me an email. Sungduk's going to industry, but there's a small group of people playing already on NERSC. You get an allocation there. The GitHub's there, and you have to shoot me an email.
And also we have dedicated like Slack channel like for ClimSim2. So yeah, if you are interested, then just please like contact me. I will add you to our Slack channel.
And we have one last question from Jerry online. How hard would it be to try to emulate radiation and convection separately online with ClimSim?
I think with the current code base, it will not be like super straightforward because the iteration MMF has radiation code working at the CRM grid scale. So our data set is targeting to emulate the whole this fees run on package that include like CRM grid scale radiation calculation. But then taking out may not be doable with the current data set. But to do that, we will need to develop new data set for that purpose.
Great. Thank you for your presentation, Sungduk.